Hi everyone! So in the first part of the video for this week, we went over what a statistical inductive argument is and how they're related to inductive probative arguments. We also described statistical syllogisms and went over some of the criteria that would be used in evaluating that particular kind of statistical inductive argument. In this video, we'll look at the other major kind of a statistical inductive argument that we're going to talk about this semester, inductive generalizations. Alright, let's get started. The second type of statistical argument that we're going to talk about is what are called inductive generalizations. So think here any sort of argument that's based upon sort of opinion polls or surveys or sample groups, anything of that sort, you're probably looking at an inductive generalization. The way these arguments work is by generalizing what's true about some small sample group to what's true, or at least what's likely to be true, of some overall population, right? So we can sort of use what's true about the sample to formulate guesses about how likely the overall population is to have some sort of characteristic. You can think about these as a specialized kind of analogical argument, because basically what we're doing is we're comparing how likely the sample group is to be representative of the overall population. So we're sort of checking to see how similar those two things really are, and if they're really similar, what's true of the sample group is quite likely to also be true of the overall population. So let's look at a concrete example of this. So let's talk about the 2016 presidential election, because this was a case where there's actually some sort of interesting things to sort of analyze how the polling data did in the 2016 election. I'm filming this video prior to the 2020 United States presidential election, so if anything crazy happened there with the polling or whatever, that's why I'm not talking about it. We just haven't seen any of it yet. So let's look. So in 2016, the sort of average of the polling, or maybe a big sample group, let's say, that there was a poll that was done that suggested that 53% of the people that were polled in this national survey intended to vote for Hillary Clinton in that election. The argument would therefore conclude that about 53% of all people are likely to vote for Hillary Clinton in the upcoming election, and so probably she'll win. And there's a good chance that you'll win if you win that large of a percentage of the vote. So notice what's going on here is that we're sort of drawing an analogy between the people who were polled and all people, or all Americans voting citizens or something, right? And suggesting that what was true of the people we sampled, 53% of them intended to vote for Hillary Clinton, would also be true of the overall population, that 53% of the overall population would have been likely to have voted for Hillary Clinton. So since this is a kind of analogical argument, like we said, what's going to matter here is how relevantly similar the sample group is to the overall population, and how relevantly dissimilar it is. We're going to use the special words of representativeness to sort of capture this. A highly representative sample group really does properly, sort of by analogy, reflect what's true of the overall population, whereas a sample group that sort of misrepresents the overall population won't give us a reliable inference to what's true of the whole population. To calculate representativeness of the sample group, there's sort of two things we're going to look at. So the first one, the sample group has to be large enough so that it's even possible for it to represent all the diversity that is contained within the overall population. So you can't. So in the case of the presidential poll, if I polled 3 people, there's no way those 3 people can represent all Americans. Indeed, probably if I polled 10 people, again, there's no way that could have represented all Americans. Now, precisely how large does the sample group need to be? Well, that's hard to say in the abstract. You actually can calculate this using math. And so since we're not going to do that, mostly don't really worry about this criteria. If there's something where the sample size is egregiously small, then yeah, we'll actually think back to some of the fallacies we talked about earlier. We can say that the argument is committing the hasty generalization fallacy. It's generalizing for a whole group on the basis of too small of a number of samples, right? Or we can anecdotal evidence fallacy if we're making this mistake because we're only sort of polling people we have firsthand experience with or something like that. But actually, you'd be surprised in a lot of cases just how small a sample can be and still be reasonably representative of the overall population. In most high-quality sort of like national opinion polls trying to gauge what the nation as a whole thinks or something, usually only 1,000 to 3,000 people actually get polled, and indeed we can show sort of mathematically that at least if you pick those 1,000 to 3,000 people correctly, they indeed could well represent the entire population of 3 million people in the United States. The more people you include, the larger your sample size is, usually the better, but there is sort of a cutoff point where you sort of have gotten enough people that it's possible for the argument to be representative. The second criteria is the one we're more going to focus on because we can do a little bit less math, basically, and sort of recognizing when the second criteria has been evaluated. So the second thing we need to be looking for and checking is whether or not the diversity that's present in our sample group actually represents or reflects the diversity that's present in the overall population. Think of the election case, right? We sort of know that different demographic groups tend to vote really differently. If everyone that was polled was from, just pick an example, California, you'd expect you'd get really, really different polling results than if we only polled people who were from Texas, or if you only polled people who were from Nebraska, right? Similarly, if you only polled men, you'd probably get really different results than if you only polled women, or the poor, the rich, yada, 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 right? So we know all of this demographic information is relevant. It's a factor in how people vote. So then we should want our sample group to more or less reflect the same demographic information that we know is present in the overall population. The same thing is true if we're doing something like medical testing. Medical testing is also kind of done on the basis of a sort of a sample group, right? A medicine is sort of given to some small percentage of people, maybe a sample group of 100 people are given some drug, and if it works for most of them, we will say that, yeah, this drug will probably work for most people, in general, most of the overall population. But if we only tested the medicine on, say, men, we'd suspect something's wrong, right? Because there's reason to suspect that maybe some drugs will interact differently with female biology than male biology, right? Or again, with old rather than just young. Again, we should suspect that perhaps the drug will interact differently. We should want the people that we're sort of giving the drug to in our sample group to more or less reflect the same ratio of male-female, young-old, overweight, underweight, yada, 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 that's present within the overall population. And ideally, these demographics will be represented sort of in the exact same proportion. So whatever percentage of the overall population is over 65, that's the percentage of the people in the sample group who will be over 65 too. If the argument fails this second criteria, we're going to say that the argument commits the fallacy of biased statistics. It didn't calculate its numbers correctly. Again, it didn't formulate the sort of percentage or didn't formulate its sample group in a way that's likely to give us reliable results about what's true about the overall conclusion. So when people are trying to carry out these studies and do a good job of it, really get some sort of representative sample group, there's a couple of different strategies that they tend to employ to try to ensure that the sample is as representative as possible of the overall population. So one thing that people often will try to do is they'll try to use some kind of pure randomness, right? So we're just sort of randomly selecting people, with the assumption being then that there won't be any sort of built-in biases in how we're selecting people if it's just random. And then you can make that even stronger if you use a technique that's called stratified randomness. This is sort of the best standards, or the best practices that you can use, where you actually sort of weigh and know the demographic information of all the people that you randomly selected, and then sort of weigh it on the basis of the demographic information of the overall population. So let's say you know that 25% of the population is over 65 years old, so then you'd only weigh the responses, the sort of randomly generated responses you got from people that were over 65, 25%, right? So you're sort of weighing that response in proportion with the extent to which that demographic is represented in the overall population. If you use stratified randomness, you can actually get by with sort of remarkably small, or sort of shockingly small samples, way smaller than you'd suspect. Unfortunately, it's often not possible to use some of these best practices. Sort of real-world concerns hamper the ability of people to always use the best techniques. For example, it takes a lot of money to do a really large sample size, right, to sample a lot of people. It takes a lot of time as well to get a lot of people to sample. And also, it can be rather difficult to get people to respond to you when you're asking people to fill out a survey. I mean, just speaking for myself, I usually don't want to be bothered filling out surveys, right? I usually got other things that I'm doing. Getting people to actually respond itself can be a challenge, and that can introduce various kinds of sort of limitations to the methodologies that people can employ in making these kinds of surveys. So frequently when we're diagnosing these kinds of surveys, we're going to note that best practices aren't necessarily going to be being followed, but we can at least sort of note how well, given the constraints that the surveyors are working from, have they sort of done their job. But even if you do follow best practices, so even if everything goes right, there's still going to be a chance of what we're going to call sampling error. So sampling error is how likely it is that just by dumb random luck even, you're going to get a misrepresentative sample. So let's do a really simple example. Let's say I'm going to flip a coin, and I don't know how many faces there are on the coin. I don't know if the coin has one face or two faces. So I'm going to flip it 10 times, and use that to try to figure out exactly how many faces the coin has. Seems like, a sensible strategy. So let's say I flip it 10 times. Each time it lands heads. Okay. So I should probably guess then that the coin only has one face, right? That both sides have the exact same face on it. It's really, really unlikely that if the coin had 2 faces and I just happened to get the head side all 10 times. But it's not impossible. Things that are really unlikely to happen all the time. They happen indeed exactly to whatever small percent chance they have of happening. And so you can always get lucky, even if you're following the best practices. And then if you have to make various compromises with your methodology for sort of practical considerations, the risk of sampling error increases. The nice thing is that using statistical methods, you can actually calculate about how likely it is that there's going to be some sort of serious sampling error. Again, we'd have to do statistics to figure out how, but indeed, this can actually be calculated. And so the way that, especially sort of really high quality polls and that sort of thing, sort of account for the possibility of sampling error, is what we're going to call the margin of error. So let's think back to that first example I gave you from the 2016 election. So the poll suggested that 53% of the people that were in the sample group were going to vote for Hillary Clinton or intended to vote for Hillary Clinton. But the pollsters calculate that there's some percent chance of just getting unlucky with the people that were sort of randomly selected, and so that there's some sort of sampling error built in. And so they might say that there is that 53% of the overall American population is likely to vote for Hillary Clinton, plus or minus 3%, let's say. Right? Where that plus or minus 3% is the margin of error. Right? The chance that maybe we got really unlucky, so in fact we shouldn't say exactly 53% because that's really precise, but something right around 53%, something a little bit more, a little bit less. And that margin of error then is supposed to sort of account for the sampling error, the sort of chance that there was something misrepresentative. And so you usually see that in polling, right? That you have plus or minus 3%. Same thing with medical testing again. It's usually that this drug will be effective on 45% of the population, plus or minus 10%. Within some range of sort of allowed error built into it. Margin of errors are a very powerful tool. The higher the margin of error is in some argument, the more likely it is that the conclusion is true. And so the stronger the inductive argument becomes, right? So let's say instead of saying that the margin of error is plus or minus 3%, that the same poll was there's a 53% chance, that 53% of people intend to vote for Hillary Clinton, plus or minus 10%. Okay, well, that's a lot more likely to be true. It's a much larger margin of error. So the claim and the conclusion is a lot less precise. There's a lot more wiggle room for sort of reality to fit within that enormous range, right? The range of 43% to 63%. It's a very large range. But also note that the arguments become, though it's more likely to yield a true conclusion, it's become rather useless. Right? If there's a 53% chance to a 43% chance to a 63% of people are going to vote for her, that covers everything from Hillary Clinton wildly losing the election to her overwhelmingly winning it, and the poll gives us no useful information. Whereas the smaller margin of error, so 53% plus or minus 3%, that's a lot closer. It gives us that the range of possible outcomes here is maybe like a really close draw, or maybe a sort of solid victory, but not an overwhelming victory. So something like 50% to 56% of people voting for her. And in fact, even though if you had to guess, you should have guessed on the basis of this polling that Hillary Clinton was going to win, and indeed, we all know she didn't, right? She lost the election. If you look at it in terms of the margin of error, the results were actually pretty accurate. The low-end possibility is that it would have been about 50%, it's about 50-50 split, and that's roughly the result. Indeed, she actually won something like 50, I think it's like 50.5% or something of the vote. So the number of people who voted for her were indeed within the expected margin of error. It's just that they were sort of from her perspective at least, the wrong states, and so she didn't win the Electoral College. Right? So, weirdly, even though the guess that we would have formulated on the basis of the opinion polling would have been wrong, we would have guessed she would have been likely to have won the election, that doesn't necessarily mean that the polling was done incorrectly. One possibility is that it could have been really, really close and then, decided by quirks of the Electoral College. Alright, so that's going to do it for our discussion of these statistical inductive arguments. We could spend a lot more time going to a lot more detail about how to do things like polling, how to go about doing things like calculating these percentages. That's just a statistics class beyond our sort of purview. But hopefully you all feel at least a little bit better about understanding arguments of these forms than you see it. what we'll do in class is we'll get some sort of very simple practice analyzing some sort of basic examples of both kinds of statistical arguments, and recognizing some sort of maybe egregious mistakes that are made in some of them. So that's what we'll practice the rest of the time. Hope you're all doing really well. I will talk to you later. Bye.